to talk today about shining light on the dark side of the universe. And for talking about the dark side of the universe, and you might have read about it a little bit in your handout, it's parts of the universe that don't interact with light. So it's perhaps a little bit ironic to say that I'm going to talk almost entirely about light. What is light? How do we see light? What sort of things can we infer from seeing light? And eventually, why that's the way that we still think about the dark side of the universe, or why we still try to learn about the dark side of the universe from light. So the first question is, how do we observe our universe? And for as long as mankind's existed, we've observed our universe by taking a telescope for our eyes, going out to the night sky, and looking up. And every time we do that, we see only light. That's the only signal that we get from our universe that we were able to see for most of human existence, is this light signal. And so if light had very different properties, we would see very, very different things. You know, how we interact with everything that's out there, or how we observe it, is only due to light. And that was true back in the days of Kepler, and that was true in the days of the Hubble telescope today, and that was true when man looked up and saw constellations. So what is light? Light is a wave that carries some sort of energy, right? And it has two properties. It has a wavelength, and it has a frequency, and those are related. And the wavelength, in the visual range, where your eyes can see light, the wavelength is corresponding to a color. Your brain interprets different wavelengths of light as different colors. So red light has a very long wavelength shown up there, and blue or purple light has a very, very short wavelength that you can see. And in top of that visible range of light, there's a whole non-visible range. There are many, many orders of magnitude of different light that you can't see with your eyes, but still affect us every day, right? So if you can see here, this is the visible range just on this little scale here. At some points in the lecture today, we're going to talk about radio waves, which are all the way down here, compared to that very tiny range. Or we're going to talk about gamma rays, which are way, way up here. And that spans different orders in the wavelength of the light of more than 14 orders of magnitude. So you're moving from wavelengths that are thousands of meters long, or to wavelengths that are, you know, much, much smaller than an atom, right? And those probe different things. Now, all of these are related to the energy of the light. Is related to its wavelength. So very, very short wavelength light has a very, very high energy. And very, very long wavelength light has a very low energy. And those are related in that the frequency of the light, which gives you the energy, and the wavelength give you some constant, which is the speed of light. A constant speed in every reference frame and in you know, every situation as long as you're looking through a vacuum. And this is one more just a little visual display here that's worth noting. Here are different things. This is the wavelength of light compared to the different objects in the world, right? So radio waves are on the scale of buildings to atomic nuclei for gamma rays. Light is composed of particles called photons. So it's a wave, it's also a particle. And that dichotomy is interesting, because sometimes you have to think of light as a wave, as thousands of photons moving cohesively, and sometimes you think of light as a particle interacting with a single atom or single particle in your existence. For instance, a sodium lamp can emit one photon that has an energy of 590, wavelength of 590 nanometers. Right? It's a single photon, or it could emit two photons that have that exact same wavelength. Sodium lights, like the ones you see in streets, emit only 590 nanometer light. But it can emit 1.5 photons that are like that. It can emit 1, 2, 3, 4. And in common practice, when you're looking up at a sodium light, you know, it emits many hundreds of trillions every second, or even more. So you don't care that it's 100 trillion in 1 or 100 trillion in 2. But in certain situations, it matters that it can only be integer numbers of photons that get emitted. This comes up in a scenario called the photoelectric effect, where let's say you had a surface material, you had some sort of solid material, and you could knock an electron off of the metal if you hit it with a high enough energy photon, right? If you hit it with a really high energy photon, it would eject an electron, and you could see that electron in some sort of sensor. This is actually how a lot of sensors that we'll talk about later actually work. Well, let's say you were using your sodium light, and it was giving you, 590 nanometers, in this case 700 nanometer light. Well, that light has an energy of 1.7 eV, which is the kind of an energy unit, which we'll talk about actually a little bit later. And that's less than the energy required to knock one of these electrons away. So no matter how much I turn up that light, as long as the energy of each individual photon is only 1.7 eV, I'm never going to knock any electrons off. You would think, well, if I can knock electrons off, I'll just keep turning the light brighter and brighter and brighter. But it's not brighter. I have to go to higher frequency light if I want to knock off an electron. So here, the amount of energy it actually takes to knock off an electron in potassium is 2.25 eV, more than 1.7. And so once I do that, I start knocking off tons of electrons. And then how much I turn up the light, as long as it hits that frequency, tells me how many electrons I knock off. And all the energy after that, if I go to, say, much more higher energy, 3.1 eV energy light, each photon is still knocking off one electron, right? So when I increased to the frequency, I didn't increase the number of electrons I knocked off. I increased how much energy those electrons had after they left, right? So and you have to think in different circumstances. Sometimes light is this coherent wave, and sometimes it's particles. And the situation that you're thinking about, determines how you think about light. But light is more than that. Light is a manifestation of an electromagnetic force, which is the force that controls most of the interactions you see between objects in the sky. The electromagnetic force is the one that tells my hands that I can't move through this table, right? It's the one that controls, the circuits in your computer or your TV. And light is a manifestation of that force. It's the one that controls lighting. So most of the things we think about in physics around us, there's gravity, which we commonly experience, and everything else almost that you commonly experience in life is controlled by this electromagnetic force, and light is the carrier of that. To be slightly technical for a minute, and this doesn't relate to the rest of the talk, but it's some interesting information, light is kind of these steady vibrations in the electromagnetic force. So if you think about, you have kind of a jump rope and you attach one side of the wall and you go like this very smoothly, right? You get these kind of coherent waves in your jump rope that you can see. And those are steady waves, and they're kind of like light waves. Now if I go like this and I just kind of jiggle it quickly, I just get this mess. And this mess is the electromagnetic field that exists everywhere in nature and controls these interactions between objects. Sometimes people talk about them as virtual photons. But they're not really photons at all. They're just jiggles in the electromagnetic field that control, there's some that get excited here as I try to touch this table that tells my hand, no, go back. You can't go through tables, right? So there's light as a carrier of the force that controls everything we see. So when we think about space, light is going to control how we view our universe, not only because it's going to control what photons I actually see come into my telescope, but if I'm looking at a star, it controls how hydrogen mixes to form helium in the star. It controls how that light that gets emitted goes through all the plasma and gets to me at Earth. It controls how bodies interact in space. Light controls kind of everything, and that's worth knowing. So here are all the particles we kind of know about up here in this corner. And nearly all of them interact with the electromagnetic force, which means they have some interaction with light particles. So how they interact in the universe is all controlled by light to some extent. The one exception, and we'll come back to it later, are these neutrinos, which are particles that don't feel this electromagnetic force at all. They are totally unaware of this field that is controlled by light and permeates all of nature. They don't know about it. And so when there are changes in this electromagnetic field, changes in those jiggles in the jump rope, they don't know. And they continue on their merry way. So we'll come back. They interact via another force called the weak force, which we'll talk about in later lectures. So how do we observe the universe with light? Well, there are two sort of things that we can observe. We can observe the things that emit light, like all these stars here, right? Or we can observe things that absorb light. If we know what the light is behind these clouds here that absorb light and re-emit different types of light, we can see the clouds. Even though they don't emit light themselves, they're changing the light that goes through them. And those are the two ways you can really observe the universe. Things that emit light and things that alter light in some way. So what can you tell by looking at a source of light? Well, there's a certain type of source spectrum of light that you can see. And it's common in everyday experiences. It's what you see when you look at the coals of a fire.
This is called a black body spectrum. So things that are really hot emit light because they're hot and they have lots of energy. And some of that energy gets emitted as light particles when there's interactions inside the subject. And it has a very specific spectrum. So here are different wavelengths here. And here is how much light gets emitted at all these different wavelengths. This very peaked spectrum. And how peaked the spectrum is and where it gets to its highest value is dependent on the temperature of the object. So if I stare at something in space, or if I just stare at something on Earth, like a fire, and I see a spectrum that looks like this, I know immediately how hot the object is. I know that it emits like a black body, and then I know what temperature it is. But there are also things that don't emit thermally. They don't emit this black body spectrum, and we interact with a lot of these things all the time, right? So these are sort of things that aren't because they're hot, but because there are certain transitions inside the material. Usually this says, let's say you start with an electron out here, and there's a proton in this nucleus of whatever material you want. And the electron used to be in this orbit, and it gets closer. That frees up some energy, right? Because the electron and the proton attract each other, and so when they get closer, they're in a more kind of preferential state. They like being close to each other, and that emits some energy. They went to a lower energy state, and so energy came out in the form of light. And these transitions give you exactly what sort of energy the photon is that's emitted. So we already talked about a sodium lamp. There are certain transitions inside of sodium that emit light that's 590 nanometers. The difference in energy between this state and this state is the same as a 590 nanometer photon, and so that's what you see. You see only yellow photons. This is a laser, for instance, emits coherently lots of photons at the same frequency, and the frequency, whether it's a green laser or a red laser, is determined by the material. You can have, X-rays that, when you break a bone or something like that, are emitted in the X-ray band and are photons predicted by these transitions. Your cell phone does the same thing. Your microwave sends out photons that are exactly at the resonance to excite water molecules, which is why your microwave is so efficient at heating up things that have water in them, and do weird things if you stick bread in or something like that. In astrophysics, we'll talk about 3 different interactions, which I'm just going to kind of throw out here, and then later lectures they'll come up all the time, so it's nice to hit them briefly. The first one is called synchrotron radiation. So this is when I have an electron that moves through a magnetic field. So if you remember, electrons interact with the electromagnetic force. Part of it is the magnetic force. And so a magnetic force spins an electron around in a circle. An electron entering a place with a magnetic field spins around in a circle. And if you think about it, every time you're spinning, you're changing your velocity, right? And so I need to conserve momentum when I do this little transition. And that conserved momentum comes out in the form of photons, which shoot out in the directions that I'm turning away from, right? And that changes the momentum of my electron and causes it to spin around in a circle. This emits photons, and then these photons go off, and maybe they go into our telescope days, weeks, years later. And they tell us something not only about the magnetic fields that the electron was going through in space, they also tell us about the energy of the electron, how much energy it had, how fast it was moving when it started spinning around in a circle. There's what's called Bremsstrahlung photons. These are emitted if I have, say, an electron that moves very quickly, and it moves past some proton or some other charged object. I have 2 charged objects, they pass through each other, they bump, they change direction. When they change direction, remember, we have to conserve momentum, we have to conserve energy. We shoot off a bunch of photons to do that. And these are, bright photons, we can see them in our telescope. The last interaction is called inverse Compton scattering, which comes in when a photon that already exists, there's lots of them in space, photon moves through space somewhere, it hits an electron, and the electron has a bunch of energy because it was moving really fast, and they bounce off of each other, and the photon gets some of that energy. So it changes the energy of the photon. Now these, I just glossed over them in about 2 seconds. We'll talk about them all in great detail, I think in lecture 6 or 7. But these are probably the 3 primary kind of ways that you observe photons non-thermally in space. You also observe the thermal photons from stars and some other things that we'll talk about. But these will all show up later in lectures. So that was how we detect different things that emit. We detect this thermal emission, which stars happen to have, which coals on your fire happen to have. We detect these non-thermal emission sources, which things like your microwave oven have. We can also detect absorption. So let's say I have a source. It's called a continuum source here. It's one of these black body sources. So a star, it has a temperature. I know exactly what this spectrum from this star is supposed to look like given the temperature. But there's some gas in the middle, right, between me and that star. And so the star is emitting light, but before the light can get to me or my telescope, it has to go through this gas. And like I said, different gases have different transitions, regions where it's very easy to excite an electron into a new state or put it down into a state. And for those frequencies, they absorb those photons very efficiently because they like to move between those states. So hydrogen gas, for instance, absorbs this specific red photon very well, this specific blue photon very well. And it doesn't absorb things as well at different frequencies. Some frequencies it absorbs differently than others. That's the whole detail. So when the light passes through, this stuff gets absorbed, the rest goes through. And then when I look in my telescope, I see the spectrum from the star minus all this stuff that got absorbed really efficiently by the cloud. I know now that there's a cloud there, and I can't even see the cloud. It's just that my star looks a little bit funny in this specific way. Okay. So different materials, and you can kind of zoom in here. Different materials give you different absorptions in different bands, and so you can know, is that cloud mostly hydrogen? Does that cloud have some iron in it? Does the cloud have some copper? Because from experiments on Earth, we know exactly what the absorption is of all these different materials, and that tells us what sort of materials are in between us and the star that we're looking at. We can use this also to find planets. This is just kind of an aside here, because I think this is a really interesting project. The Kepler Space Telescope was launched in 2009. It's still going today, detecting planets. And the way it looks for them is it can see the star. The planet is really, really dim, so you can't see it from Earth. But every once in a while, if you have a star that's aligned the right way, the planet will pass in between you and the star, right? So you're looking at the star, but a planet got in the way. And the planet's not very bright. So that actually decreases how much light you get from the star. And if someone who's near that computer could really carefully click that button there. There's the play button. Yeah, I can run a video. Not a problem. Sorry to sneak through. I realized I can't run a video down there. There we go. Not a problem. So every time this planet, you can see how much light you get from this star here. It's a function of time. And every time the planet goes in front, you get a dip. You get less light from the star than you used to. And that happens the same because the planet orbits every month or every year or something like that. You get these characteristic dips that you can look. You also get a little dip because the planet makes a little bit of light. And so when the planet goes behind the star, you're missing that light, which isn't very much. But you get these two characteristic dips. And so you know that there's a planet there. And this was really exciting over the last couple years, because a decade ago, we didn't know of any planets outside of our solar system, really, or maybe 2 decades ago. Then we knew of a few, and we didn't know how lucky we were. And for years, theory had said it's almost impossible to form planets. All the planets fall into the star really early on. You don't get any planets. But now that we know from looking out in space with this telescope that there are billions of planets just in our galaxy. Hundreds of millions to billions of planets. And almost every star has a planet. The theories aren't quite right. And that's all because we can look at light, we can look at things that are absorbing light, even though we can't see the planets themselves. And absorption really depends on the wavelength of light. Different light interacts with different materials and is absorbed the same in different ways, right? So, for instance, when you go under, say, a tunnel or something like that, or let's say you're downtown and you go into your parking structure, for a while your AM radio still works. Your FM radio actually cuts out much earlier, but your AM radio is still going as you go deeper into this tunnel. And that's because AM radio waves have a really long wavelength. So you get through lots of material very efficiently. They're not stopped until you get through lots of concrete. So you can still listen to your radio for a while, even though you can't see the station that the radio beam is being broadcast to. The light's all been blocked. The FM radio has been blocked. But the AM, because it has such a low wavelength, gets through. If we look into, say, the center of our galaxy, that has a big impact. there's so much gas and so much dust that a lot of those wavelengths of visible light are absorbed very efficiently. And so what you see when you look at the center of our galaxy, because there's so much gas and dust and other stuff in the way, is you don't actually see visible light coming from the center of our galaxy. It's absorbed very well by dust. But you do see things like radio waves or gamma rays that aren't absorbed so well. So just because of the properties of this medium you're looking at, you have to look at certain wavelengths if you want to see the center of our galaxy or if you want to see a specific source. I should say, as kind of a note, light tends to interact very efficiently with things that are on the scale of that wavelength of the light. That tends to be a good rule of thumb. So what else can we do with light? We can see things that emit light. We can see things that absorb light. We know something else about light. It moves at a constant velocity, c. And this is actually, I think, one of the most astounding things in astrophysics, right? Because we should be able to look out and we should be able to see how our universe is today. But in fact, we can do so much more than that in astrophysics. Because when we look out, we're not seeing the universe as it is right now. We're seeing it as it was when that light was emitted from whatever object the light had to travel to us from. So as long as the light was able to kind of stream through space freely, not be absorbed in the process or emitted, then you're looking at things how they used to be. You look out at the sun, and you don't see the sun as it is right now at the sun. You see it how it was 8 minutes ago when that light left the sun. And the sun is 8 light minutes from us, which means it takes light 8 minutes to get to the Earth from the sun. So, if the sun suddenly disappeared for some random reason, we wouldn't know about it for 8 minutes, because everything has to travel at the speed of light. And we won't know until suddenly things go dark 8 minutes later. Okay, 8 minutes is great. The universe 8 minutes ago is about the same as the universe is now, and probably, I hope, about the same as it's going to be 8 minutes from now. And so that doesn't tell us much about the universe. If we look at, say, Alpha Centauri, that light takes 4.4 years to get to us. So that tells us how the universe was 4.4 years ago. On properties of the universe scale, it's still about the same. If we look at Andromeda, it's 2.5 million years ago. Universe is about the same, but that's telling us something different about when the universe was slightly older. But we can look way, way back. I'm going to do this cool zoom in here. Okay, I'm proud of that. So we're going to do this zoom in. We're looking now, this is what's called the Hubble deep field. I show this in basically every public talk I give, and I might show it again to you. We found the darkest spot in the universe where we couldn't find anything that was close to us. We thought there was nothing there. And you pointed the Hubble telescope at it for a long, long time, where you didn't think there was anything, and this is what there is, right? So there are no stars in this. Every single one of these is a galaxy, essentially. And they're all at different distances. Some are only hundreds of millions of light years away. Some are billions of light years away. You can see some cool galaxies here. There's a galaxy that's on its side over there. There's one. And like this thing here, this little red dot that you might not see in the back, is a galaxy too. So thousands of galaxies. This little patch of the sky is smaller than the full moon in the sky. So if you look at tons of full moons in the sky, there's hundreds of millions of galaxies out there. It's pretty incredible. Okay, we'll zoom out. Cool. This was recently spotted. This is the oldest known galaxy at this point. It's this little dot that you won't be able to see here, but they were very nice and blew it up for us in this picture. This is a galaxy that is 13.4 billion years old. The light's been traveling to us for a very long time. And this galaxy, we're looking at it now, not as it is today, but as it is when the universe was only 400 million years old. Right? The universe now is about 13.7 billion years old. We're looking at how galaxies looked when the universe was only 400 million years old. And that tells us something really interesting about how galaxies formed over time. I can see every stage of how galaxies formed just by looking at different distances away from us. And that's astounding. And the first thing you notice when you look at this galaxy is it doesn't look white, it looks very red, right? And that's not what you expect. And that's due to something called redshift, which is as you go farther, the universe is expanding. And that will be talked about in great detail in the next lecture, but we'll just take that as kind of an adage for right now. The universe is expanding, so you can kind of think of it roughly as the universe is kind of a surface of a balloon, and the balloon is expanding. You're blowing up the balloon. What that means is that all the points on the balloon are getting farther away from each other as you go from here to here. And so if I have a wavelength that started like this, it started very blue with very small wavelength. The wavelength got bigger in the expanding space. That's not 100% physically true. We're not on a balloon. We're in a universe. But it's a good way to think about things to get the right kind of opinion. So light becomes redder as the universe expands. And how do we know what the redshift of something is? Well, let's go back to those absorption lines we talked about earlier, right? So chemicals, hydrogen is the same hydrogen 400 million years after the universe was formed as it is now. So it absorbs and emits light at those same specific wavelengths that we know about in our lab. But after that light gets absorbed or re-emitted, it now has to travel all the way to us. The universe is expanding, so those lines get redshifted. So if I look at a star, here are some very specific lines that I see from that star, from different absorption. And if I look back at a galaxy that's a little bit farther away, all those lines got a little bit redshifted. Because as the light was traveling to us from those, the wavelength of the light changed. And so all my bands shift like this, and that tells me how far away the thing is. Right? If I go to really, really early galaxies, these ones shifted all the way off the page. This one over here becomes this one is this one, et cetera, et cetera. And I know the distances between all these, so it's just like putting together a puzzle now. And I know exactly how far away that object is that emitted light. And that's a powerful tracer of how far different objects are in space. We have a handle on how distant some galaxy is by knowing where all these lines are and where they're supposed to be. This is so useful that people don't talk about galaxies being 100 billion or 100 million light years away or 5 billion light years away. That doesn't come up in science. What comes up is the object is at redshift of z, and z is the observed wavelength of the light divided by the emitted wavelength of the light minus 1. So the wavelengths got longer. It went from here to here, so this is some number that's slightly greater than 1. But if our sun is at redshift 0, which means the observed wavelength and the emitted wavelength is about the same, and that gives us a redshift of 0. That object I showed before is, I think, at redshift 9 point something, which means that all these things are shifted over basically by a factor of 9. And that's a very old object. Okay, so how was the expansion of the universe in redshift discovered? Edwin Hubble first looked at this in 1929. I got that right. 1929, and when Hubble looks at this, and he sees that different objects have these different characteristic redshifts. They're different distances away. Here's his data. It looks totally sloppy. I'm not exactly sure how he discovered anything from this, because kind of like this, and it wouldn't make a lot of sense. But Edwin Hubble was the best astronomer of his day. Everybody decided that. And so when he said there was redshift, everyone was like, aha, there's redshift. So he has this nice plot of how far away he thinks the object is from other observations and how much this thing redshifted. Here's what the data looks like today. Now I can look at the data and be like, oh yeah, there's some redshift right there. Yeah. Here's the line as things get farther away, how much they shift away from us, how much they redshift goes up. And it's a very nice linear thing with lots and lots of galaxies detected in different types of surveys. And so that gives us, the slope of this line gives us Hubble's constant, which is, given how far this object is away, how fast is it moving away from us? And the farther and farther an object is away, the faster it's moving away from us because the universe is expanding. Right? So the point that's very close to you on the balloon is moving less fast away from you than the point on the other side, which is moving very quickly away from you. And this Hubble's constant, the slope of this line, is 70 kilometers per second per megaparsec. And a megaparsec is like 3 million light years. So every 3 million light years you are away from an object, it's moving 70 kilometers per second faster away from you. Or it looks like that due to the expansion of the universe. So if you go to an object that's 60 million light years away, it looks like it's moving 20 of these, so it's moving 1,400 kilometers per second away from you. I think I did that right. Great. Pretty exciting stuff. So what else can that tell us? That can tell us where all the gas is that's absorbing from some sort of background source. So we have a source that's at some redshift, and we look at it, and it has the redshifted photons, but it also has different absorption bands that happened at different times as the light was traveling. It's somewhere in the middle, it hit some gas, and that gas absorbed at whatever redshift it's at. It absorbed however it absorbs there. And then that light only gets redshifted by the difference between us and that new gas in the middle. And so that tells us we can get a whole 3D map of where all the gas is everywhere in the universe by taking light that we know how it was redshifted from way back and using it as a backlight. And just at every different point, there's absorption from everything it went through. And then once it goes through something, you redshift that light back to Earth, and then you look at it in your telescope, and you get, here's how the whole universe is structured in 3D. It's incredible. Okay. So now we talked a little bit about how we use redshift, what we can see. Now I'm going to talk about the first photons. The photons that come from what we call the cosmic microwave background. What they are, what they can tell us. This will go into a lot more detail in the next lecture, but I'm going to start here. So the universe starts off and it's very, very, very hot. It has a high temperature. Millions of degrees, and then cooling to tens of thousands, and eventually thousands of degrees. When something is thousands of degrees, there's so much energy, so much bouncing around, that electrons freely bounce away from nuclei. So you have what's called a plasma. You've seen it. Plasma can be formed in these little plasma balls that were popular in the 80s or something. So you have all this plasma. It's bright. You'll notice the thing that you see from plasma balls is you can't see anything behind them. They're opaque because light that's going through is very efficiently absorbed because all the electrons and protons are free. And they're just bouncing around as charged particles. They absorb light very efficiently. So any light that you had at the beginning of the universe when the universe is hot just bounces around. It gets absorbed, it gets re-emitted, it absorbs, it re-emits, it absorbs, it re-emits, thousands of times a second. So you don't see any of that light. It's just constantly getting changed by interacting with materials. Finally, the universe cools down, and I think that maybe is the next slide. Finally, the universe cools down, and the electrons and protons combine. And once they do that, there's something that's a neutral thing overall, right? There's an electron with a negative charge, a proton with a positive charge. They're neutral. They don't absorb light as efficiently anymore. Suddenly, you're in a situation where light has been bouncing around for the entire beginning of the universe, the first 400,000 years of the universe, in fact. Light is bouncing around, thousands of times a second. And suddenly, once it bounces off something, and then it doesn't get absorbed again. It never goes through more ionized gas because the universe has cooled down. As soon as it goes through something, it goes all the way to us. And it travels from when the universe was 400,000 years old to our telescope, and it doesn't interact anymore. So that light is powerful. I mean, it tells us something about how the universe was when it was 400,000 years old, the last time that light interacted with matter. And if you look everywhere in the sky, you see, this is green, so that every direction I look in the sky, I see this same light. Right? And that light looks like a black body. And the reason was it was the temperature of that gas. It was a hot gas, and that's what was emitting photons. 3,000 degree Kelvin gas was emitting all these photons. So it looks like something that's 3,000 degrees. And then it redshifted, right? Because it was very, very early in the universe. So the wavelength stretched out from 3,000 degree black body light. So there's my 3,000 degree light. And now it cooled. I mean, basically this black body shifted over. All the wavelengths became longer, cooler. And what we see now is a black body that looks like it's 3 degrees Kelvin. Actually, I think 2.5 or something like that. It's almost absolute zero. It's very, very cold. That's like negative 440 degrees Fahrenheit, something like that. So it looks like a black body emission that's very, very bright, but very, very cold. In every direction we look in the sky, we see the same 3 degree light. Great. Oh, yeah. That also tells us, right, because it went from 3,000 degrees to 3 degrees, the red shift in those units of the cosmic microwave background is 1,000. Okay. So just a little history lesson, because I always think this is funny. There was a theory written down by some guys that said, hey, the universe started really hot, and then it cooled, and then you should see this black body radiation every direction you look. One of the people who wrote this down is Robert Dicke in the 1950s. So finally, Arno Penzias and Robert Wilson in 1964, they were working at Bell Labs in New Jersey, and they had a radio telescope, and they wanted to look into space and see cool things. In every direction they pointed, they saw this background that was like 3 degrees Kelvin, and every direction they looked, they kept finding it. So they decided, we're in New Jersey, it's too close to New York City. New York City's emitting stuff that's 3 degrees Kelvin, and we're just seeing it every direction we look at it. So okay, let's point towards New York City, let's look away from New York City, it'll look different. And it didn't look different, it looked the same. So then they decided it was the cosmic microwave. No, then they decided, aha, there were a lot of birds in New Jersey. And when there's lots of birds, they eat bread, and then the bread, you don't have to fill in the details, and that gets all over our telescope. And so they wrote a paper, or like a little note on radio emission from birds, eating bread, and then et cetera, et cetera, et cetera. So they set up bird cages all through New Jersey around their telescope. This is a true story. They set up bird cages, they tried to catch all the birds. They tried to clean off the telescope really well. And then they pointed it in space, expecting this to go away. And still, they looked this way, they got 3 degree emission. They looked this way, they got 3 Kelvin emission. Every direction they looked, and they were utterly confused. And so they eventually, some word got back to Robert, who said, I predicted this 5 years ago. This is what it is. It's a cosmic microwave background. It's the most exciting discovery ever. It's worth the Nobel Prize. And that Nobel Prize went to bird dropping guys. Not to Robert. I tell that story like these guys didn't know what they were doing. They're very good radio astronomers. But they also got a Nobel Prize, so they can deal with me making fun of them. Also, cool thing. When you had an old TV that was analog and you turned it to a channel where there wasn't anything, you saw all that crazy static. About 1% of that static is the cosmic microwave background. It's about at the right energy. It's really bright. So that there was also a bunch of other stuff from whatever city you were next to. But also cosmic microwave background made some of those pixels black and white. So like I said, every direction you look is about the same. And that tells us something really cool about the universe. We're not in some special place that we're near one side of it. We're in the middle of the universe, and because it's an expanding universe, it turns out everybody's in the middle of the universe. But there are little differences, very slight differences, on the order of 1 part in a million in the temperature of this cosmic microwave background. And so what I told you about redshift earlier is that, remember, hydrogen works the same. Things change from this plasma state that absorbs photons to a state that doesn't absorb photons, and they do that at about the same temperature everywhere. And then they redshift all the way here. So what it tells us is that certain parts of the universe change from plasma states to this kind of free molecular state where the light can move at slightly different times, 1 part in a million different times, right? And so when you look at this with a really high-resolution telescope, this is the Planck telescope here, see these little patches. And I think this is backwards from my six. The blue patches are hot because blue light is hotter, and the red patches are cold. And that tells us, different temperatures when we look different places in the universe. And like you said, on the scale of 1 part in a million. So it's almost the same temperature everywhere. Very fine differences. And this tells us a lot about how the universe formed. This is extremely interesting because the universe started from a bunch of, it started almost the exact same with very, very small fluctuations. And those fluctuations depend on quantum mechanics and tell us about things that happen at the very earliest part in our universe. And we know we have a theory for how those fluctuations grow out to 400,000 years afterwards, and then we can see the light and test our predictions by seeing how those fluctuations grew and impacted the universe. Here are our predictions. This band is our predictions, and what this is at different angular scales. Like if I look at a hot part of the sky here, how far do I expect it to be to the next hot part of the sky? So it's the angular scale between different parts of the sky, which is detailed. You don't need to know too much about it. Here are our predictions in these bands. Here is the data. There are error bars in all of this data. There are really, really small, perfect error bars, and everything is amazingly well fit. This also got the Nobel Prize, and probably we'll get more. So then once you get out to here, the data gets a little bad, but the predictions are still being perfectly fit. Here are the different telescopes we've used to try to kind of find these different angular correlations, or these different patches of hot and cold on the sky. This is the Kobe satellite in the 80s and 90s. And you can see it doesn't see much about the difference between hot and cold patches. It doesn't see it with good resolution, and it doesn't see a whole lot of differences. That was the best we had. That was actually enough to get most of these points down here. Then we launched the WMAP satellite that operated in early 2000, and it saw these hot and cold patches much, much better angular resolution. Planck, which launched in 2009-ish or so, 8 or 9, it just actually finished its science mission, although we're still looking at the data from it, found this much better angular resolution stuff. Here's what the whole Planck sky looks like now. So different hot and cold patches tell us a lot about physics. Here's a slightly technical thing, which some people might find interesting, some people might not. How these different hot and cold patches form is, what you think about is there's two forces at play, right? There's all this plasma, and the plasma has positive and negative charges, and it's emitting photons, and that pushes things away from it. Because you emit a photon and it zaps something, and it pushes that other object away. You also have gravity, and gravity is trying to pull things together. So if I have an area that starts a little bit more dense than another area, there's a little bit more matter around it, there's two forces at play. There's the photons that are in that area are trying to push everything away, and gravity is trying to pull everything else near and towards those hot clumps. And so that gives us an area where there's kind of a fluctuation. Things get overpressured, and then they get pushed out, and underpressured, and there's a balance, and it goes back and forth. It actually looks like a sound wave, with high pressure areas and low pressure areas that are acting. And so those high pressure areas stay hot, they absorb light for a little bit longer, and they become the hotter areas of the sky. The slightly lower pressure areas become the cool parts of the sky. This will be talked about next lecture. I just kind of wanted to show it real quick. One other thing you can do with the CMB, you can learn all this stuff about how the universe was when it was only 400,000 years old. But in keeping with my what does light tell us and what does it tell us about things that absorb light, there's one other cool thing you can learn, and it's called the Sunyaev-Zeldovich effect, found by those two guys. So you have the cosmic microwave background is not only one of the most interesting sets of photons from the sky, it's also the perfect backlight, right? Everything that we look at in the universe happened basically after the CMB, everything that we can see light from, and the cosmic microwave background is in every single direction of the sky. So any object I look at, I can not only see the light that it emits, I can also see what it does to the cosmic microwave background that had to move through it to get to us, right? So if I look at really, really large clusters of galaxies that are really, really far away, well, there's a CMB that's still behind them yet, and it emits photons. And those photons go through this really large cluster where there are lots of hot things, high-energy electrons and stuff like that. Those high-energy electrons do that inverse Compton scattering thing that I pointed out before. The high-energy electrons in the cluster bump my CMB photons, and they give the CMB photons more energy. So they took a photon that was some, relatively cold CMB photon and made it really, really hot again. And what that looks like is that now the photons from the CMB that go to my telescope, there's less of them, because a lot of them got absorbed and knocked up by this cluster. And so now they're not in whatever, they're at a higher energy, they're not what my instrument is looking at anymore. So they look like dark spots on the CMB. So I have my CMB, it has all these little things. It also has dark spots just because there's stuff in the way that was blocking it. And this is a great way to lens and kind of investigate really, really distant clusters. And what's coolest is that what happens doesn't depend on how far away the cluster is away. If the cluster is right in front of the CMB, it's really, really, really distant, I can't see the cluster itself, but it still took all my CMB photons and it knocked them up to a new energy. And so I can see the backlight, if I put if I'm trying to show my laser pointer at the wall, it doesn't matter if the thing that's blocking it is right here or it's all the way against the wall. It's blocked the same way. And so we can see any cluster that's big as far out as they go, right? All the way out to the CMB. And that's pretty exciting. That's a new way to look at the universe using the cosmic microwave background. So now, in these kind of final minutes I have left, and I'm sorry I'm going a little bit over because I started late, because projectors and stuff are more complicated than physics. The dark side of the universe. What I've talked about here is how things interact with light. And the things that interact with light is this everyday matter that you see, the stuff that makes up the table, the stuff that makes up stars, the stuff that makes up you. And that actually only composites about 5% of the total universe. Just like you have this, the oxygen you breathe is only 21% of the total gas you're breathing in. And then there's nitrogen, which is important, which is most of the gas, but it doesn't interact with how you breathe, right? It doesn't matter. Well, it does matter. It composes most of our atmosphere. It does other things. But if you just needed to know, well, how do I breathe? You could ignore that 75% of the atmosphere. So it's the same way kind of with this dark side of the universe. These baryons are most of what's important to us in everyday life, but they're only 5% of the total universe. And the other 95% is dark. It doesn't interact with this electromagnetic field Photon is based on. 21% of this universe is called dark matter. And that will be the subject of most of our talks. I'm mostly going to focus on dark matter because that's what I do. And 75% is called dark energy. So do I have, okay. So dark matter is a force, and I kind of talked about it briefly on this slide. Like I said, this will be all the next lectures. Is a particle of some sort. It has a lot of mass, but it doesn't interact with light. And because there's more mass in dark matter, 21% to 4%, compared to how baryons and how all the stuff we can see works, it mostly controls how gravity interplays between different objects. It still interacts with gravity, it does interact with light, but most of the gravitational force in our universe is due to dark matter. And so it controls how galaxies form, where they form, how galaxies interact with each other, etc. There's also dark energy, and much less is known about dark energy. And it's there's not much of it in any small region. So I think I put somewhere the dark energy inside of the Earth is 1,000th of 1 gram of dark energy. But it's everywhere, and the same constant everywhere in the universe. What we think is interesting about dark energy is when space expands, like that balloon, if you have, let's say you put some putty or something on the surface of the balloon. As the balloon expanded, the putty would become more dispersed. It would make a thinner film. There would be less mass in putty per part of the balloon. And that's what the matter we can see, the visible matter does. That's what the dark matter does. That's not what the dark energy does. It's a point, it's part kind of the balloon itself. It's a field, we think, or at least the simplest explanation we have is that it's a field that is everywhere in the universe. So the amount of dark energy in every part of the universe stays the same when it expands. And since the universe has gotten really big lately, that was a joke. It's now 75% of the total energy. So how do we see this dark stuff that doesn't interact with light? And that's where I'm going to kind of close this lecture. So remember that discovery of neutrinos that I talked about later. So there are also neutrinos, and they don't interact with the electromagnetic field, and we've known about them for some time. So how did we detect them if they don't interact with light? Well, they do interact with something called the weak force, which is another field like an electromagnetic field, except it's weaker. Weak force. And so very, very rarely, most particles that have a weak interaction, in fact, actually, all these, like when I touch a table, there's this electromagnetic force that's telling my hand to stay away. There's also a weak force that's telling my hand to stay away, except it's like 10,000 times weaker. So most of it is the electromagnetic force. But the neutrinos don't see the electromagnetic, they only see the weak force, which is very weak. And so they mostly just move through materials, but once in a while they interact with a material and bounce off. The same way you would do with light and the electromagnetic force, but much, much more rarely. So you need these big sensors. This is one, this is Super Kamiokande in Japan. And so there are all these little things that detect light, and they are in a big tub, and you put a bunch of really clean water in this tub, and a neutrino comes through, and once in a while it bounces off the water. But I said these detect light, which is interesting. They don't detect neutrinos. So what happens is the neutrino hits something in your water. It hits a proton. It turns that proton into a neutron for particle physics reasons. And it emits a positron, which is an antiparticle of the electron. I can't detect anything that happens in this interaction really easy. But what I can detect is that my positron then goes off and it hits an electron and it blows up, and they both annihilate and they produce light. So this interaction doesn't produce any light that I can see, but this thing is a particle that eventually produces light that I can see. And so that's what I'm searching for, is the light that gets emitted when this positron hits an electron later on. So despite the fact that this doesn't interact with light, I'm looking for its light signature from this much rarer interaction. Finally, we think in the early universe, these different forces were kind of the same. This I'm going to go off on kind of some sort of metaphysical tangent. So we think there's an electromagnetic force, we think there's a weak force, and we think if you go to really high energies, they're the same force. In fact, I think we kind of know that at this point. And then we think all these forces at really, really high energies kind of work the same way. That's kind of our fundamental theory of things. What that means is we think things that interacted via the weak force, when the universe was really, really high energy, it was like they were interacting with light, or efficiently, in some sense. And so that means that in the early universe, this dark matter or dark energy that didn't interact could interact and could leave imprints on the things we see today. And so I'm going to close with that. And so that's the light side of our universe. For the next 8 lectures, we'll talk about the dark side of the universe. We'll talk about all these tricky things that we're trying to observe that are on the cutting edge of science. Everything I talked about here has kind of been decided in the last 100 years or so. But it's important to remember that every time we think about the dark side of the universe, basically every experiment we have comes down to how we detect light, how we can interact with light, what sort of detector we can build to see light in an efficient way that allows us to understand what's happening in these particles that don't interact with light at all. So as a roadmap for upcoming lectures, I will be gone the next 2 weeks, as a note. So there's going to be 2 fill-in lectures. The next one will be dark energy and what is it from the theory side. That will be given by Elise Jennings, who gave one of the lectures last spring. She gave the lecture series, and I filled in for her once. She's filling in for me once. Great. The lecture after that will be experiments that detect dark energy, and specifically the dark energy survey experiment given by one of University of Chicago's own representatives to the dark energy experiment, Keith Bechtel. He's a great lecturer, so you should come and see it. He's also a great marathon runner. He won that Chicago half marathon last week. I don't know, concerned about running or something too. And then I will be back for the rest of the lecture series, and we'll talk about what dark matter. So these 2 will be on dark energy. It's not what I specialize in, so they will be giving them. Then we will talk about dark matter for the rest of the time. First, we'll talk about why we know that dark matter creates most of the mass of the universe. We'll talk about how particle physics predicts some sort of dark matter particle. And then we'll talk about how we can detect it in the sky, in underground labs, or in particle accelerators. So thanks for attending. Have any questions? Sorry, I went over on time.
Will your slides be available on the internet?
Yes, they will be available on the internet. They're being recorded. Also, if you Google my name, first you will find an internet marketer. But if you Google my name in physics, you will find me. And I will post all these online. I have something on the top called Compton Lectures. It's not there yet. It should be by the end of the day. Yes?
So on your photoelectric effect slide, you had a photon graphically illustrated with what I believe people generally call a wave packet, which had increasing and then decreasing amplitudes.
Yeah.
And I have 2 questions about that. One is, what is intended to be conveyed by the fact that the amplitude of the wave increases and decreases? And then secondly, earlier you said something about when light appears as a wave, you said something about the wave is a result of the fact that a lot of many photons are propagating cohesively. And how does that wave with many photons correlate to the single one with waves?
Right. So light is both a wave and a particle. And when I talk about does an individual photon knock off something in the material, that means that I have to have one photon that has an energy, and energy is inversely proportional to the wavelength. Can you guys hear me? Okay. Energy is inversely proportional to the wavelength. So I need to have a single particle with that sort of frequency, with that sort of wavelength, to be able to hit that electron and knock it off the material. So it doesn't. So when you had a bigger wave like this, it still had the same wavelength. And if all of those wavelengths are not fast, small enough to knock off electrons, no electrons will be knocked off, no matter how far the wave goes up and down. And in that slide, the kind of intensity up and down was how many photons there were.
So it's not a single photon that you're trying to depict.
Right, so it's a little tricky because there's both, in that sense I was looking at many photons that are kind of traveling. But every single photon also does this independently. So the wavelength shows me two different things. For all, when I'm looking at many photons together, it's just what is the wavelength, what's the energy of those photons. When I'm looking at a single photon, it's actually as a function of time, which direction is the excitation of the electromagnetic field. And that's what the wavelength is supposed to illustrate. So people use that interchangeably, and I think it's confusing. But photons have individual wavelengths, and groups of photons have.
Could you say that again? The last part about the direction of the polarization.
So let me try to break this one. So if I have the photon traveling towards me, it travels like this, and it excites the electromagnetic field in a specific way that looks like this. So the electric field is pointing up, and then it's pointing up less, and then it points down less. So the electromagnetic field has a direction. And so at different times, as the photon is traveling, the electromagnetic field from a photon points in different directions and to different amplitudes. It looks like this time. And how fast this changes is the wavelength of the photon.
And how many of these wavelengths? I presume there's a beginning and an end. You turn the light on, it starts. You turn the light off, it stops.
Yeah,
how many?
No respect, no
respect. So for normal light, like coming from that, I have a
Going to the coffee shop? Going to the coffee shop?
Yes. I have a question.
They're
Is
not
the
coherent.
Open University of the
In a
Left
laser, they all
having a
start
talk
to move
today?
the laser like this.
You said-
They go up and down together.
Pardon?
Which is why the laser stays pointed, directional, and very bright.
No, but my question is, if you conceptualize
I
a
don't
single
think so
photon,
today, no?
You've got these waves with the
Last
variation
time we
in the
were
strength
there,
of the
October
field.
4th, 2:30,
How many
they
of
had a
those
talk
do you
on
need before you say, how many
fascism on Ukraine.
wavelengths
Well,
make a photon? Is it
yeah,
one?
we will
Is
look.
it 20? Is
Oh, I see. I see what you mean. So if I have my light and it starts here and
I
it
don't
stops
remember
here,
receiving the
is it a
notice
photon?
today.
If it
Well,
is,
if it's
I'm
less than
liable.
one, it
I'm
seems
gonna
like
have
it
to go up
couldn't
there
be.
and
It has
see.
to be,
Okay, yeah,
either,
we'll go
it has to
then.
be one exactly and not two.
Yeah.
like to go
So
too.
mathematically, it doesn't matter.
You can look it up.
In terms
Yeah.
of what do we call a photon, I would just say any between. So the question is, I have the question is the same as I have my rope on a wall and I'm waving it. When do I say that there's actual like a wave like this, and when do I say that I'm so close to the wall that I'm just moving the rope over, right? And there's no clear answer, and the math doesn't matter really when I'm changing. So the question is, what is an actual photon, and what is just some excitation of this magnetic field that just kind of messes around in some direction? And it doesn't matter what I call it mathematically. I treat it the same way. And that's why these excitations are called virtual photons. But it does matter, for light that leaves that light over there, when it comes to my eye, it's many. This wavelength is like 400 nanometers or so. So, the light from me to there fluctuated like this
Yeah, I'm
a
not
million
worried about
times.
the many, I'm worried about the one.
Yeah, the one, it's tricky. There's no clear answer.
The amplitude of the single photon can be higher or lower. Is that true?
Amplitude? No. The amplitude of the single photon is, it doesn't actually matter. The relative thing matters. So this is given by h bar times the frequency of the photon is its amplitude.
So the strength of the electromagnetic field is not influenced by the photon, or
The strength of the electromagnetic field, I mean,
it's pointed, the amplitude indicates the direction in which it's pointed, but that doesn't indicate the strength at all.
So for every photon, for people who like math, the area under this thing is the same, the integral, which means that if I had a photon that had a higher energy, it would look like this, where this peak would get higher. But this peak getting higher is the same thing as measuring that this went from here to here, and that's how it's normally done.
So if you can change the amplitude without changing frequency,
You would have two photons.
it's not quantized.
Yeah. It has to be quantized to this. Yeah, that's exactly it. It has to be quantized to this area.
It has to be without frequency.
So it's dependent on frequency in the same way. Take your other question, and then I'll go with it.
Gravity affects the light. I mean, the mass, visible mass is raised gravity.
Right.
Now, invisible dark mass, does it also affect the light the same way?
Through gravity, yeah. And I was going to put this slide in this morning in my 15 minutes before my projector died. So that's a great question because I was thinking on the way here. I should talk about that too. So let me just talk about it. I have my backlit source. I have some star here. I'll just make it look like a star. Right? And I'm here looking at it. And here there is a bunch of mass. And it doesn't matter if that's dark matter or whatever, or a black hole. Well, normally what would happen is this light would go through here. Let's just call this a really heavy billiard. A black hole for the billiard. This light would go through, but it gets blocked. But what does happen is the light that goes this way gets curved, because light moves at a constant speed and it reacts to gravity. And I see this light, and I see this light. So this light, which was supposed to go like this and miss my telescope completely, gets curved and it comes back to my eye. And so instead of seeing a star, so I wouldn't see a star something like this as a circle in my telescope. Instead I see something over here, and something over here, and something over here. I see like the edges, all this light that gets curved back. And this is called an Einstein ring. It's this kind of like circular thing of light around the halo that you can't see. So gravity can affect how we see light. And so in the same way we use that Sunyaev-Zeldovich effect to see things that were getting in the way, we can see things that get in the way through this. So we look at a galaxy that's really far away, and if there's any heavy thing that we can't see in between us and that, we'll see this curvature. And that tells us a lot about how gravity works.
Why didn't quantum physicists discover dark matter and dark energy independently of astrophysicists?
Well, the particles themselves, so a particle accelerator, detects light. It detects either charged particles that emit light when they go through material, that Bremsstrahlung radiation, or it detects light that gets emitted in your interaction and goes into your detector. So it's difficult to see dark matter particles. The way you would see them in a particle detector actually is like this. I have two particles that come in and they collide in a big particle detector, right? And they make new particles. One of them goes this way, and one of them goes this way. And the reason one of them goes this way and one of them goes this way is that momentum has to be conserved, right? If I have a billiard ball and I bounce it off another billiard ball, if one goes one way, the other goes the opposite direction, so that the total momentum is conserved. Well, and then my detector is out here, right? It detects both these particles. It says, hey, I had an interaction between something here, and it made this stuff. Well, if one of these is dark matter, I don't see it anymore, because it doesn't interact with the light, so it just goes straight through my detector, goes on into space forever and ever and ever. So what I see is an interaction that made a lot of stuff that hit my detector up here, and nothing that hit my detector down here. It doesn't look like momentum is conserved anymore. It looks like I hit two billiard balls together and they both went the same way to the left. That can't happen. And so I say, hey, there must have been something else that came and went that way. And it must have been something that was a type of particle that I would miss. And what type of particles are those? Well, there are neutrinos. That's how neutrinos were actually discovered. And they were proposed earlier. That's how they were discovered. And then you would have dark matter or something like that. So you would look for those sort of interactions. But that's really tricky, because there's a lot of other reasons that you could just miss something in your detector.
Thank you very much.
How,
Yep.
No one's? All right, I'll try again.
Was there someone else?
I don't want to monopolize it if someone else.
Oh, sorry.
Yeah, I was going to ask you, how big is the universe if you have dwelled into that question?
Sure. So the universe is, the better question is how old is the universe? And that we have an answer that is a single number. It's 13.7 billion years old. Maybe 13.6, something really close to that number. So that's how old it is. And so light can travel from the beginning of the universe for 13.6 billion years. 13.6 billion years, I think it does. Now there is a question, right? So let's say that I have that 400,000-year-olds, that universe we saw when it was only 400,000 years old, right? That means the light's been traveling to us for 13.2 billion years. Or sorry, not 400,000, 400 million years old. The light's been traveling to us for 13.2, is that right? Okay. Billion years. But how far is this galaxy away from us now? Well, the universe has been expanding that whole time, which means that this universe might have been going the opposite direction than we've been going. I mean, it's been expanding, well, it is, because everything's expanding away from everything. It's going the opposite direction, and we've been going really fast. So that galaxy now is actually something like, 30 billion light years away. 30 billion years, right? So what that means is, it emitted light when it was only it emitted light, the light traveled 13.2 billion years before it got to us. That year, we'll never see that galaxy again as it is today. Right? Now it's too far away. The light gets expanded away from us almost faster than the speed of light. It's gone. We will see how that universe continues to evolve. We'll see how it was at this point. And now it's much farther away than the light only had to travel a fraction of the total distance it is away now. So distances are kind of tricky, and it sometimes depends on which type of distance you're trying to calculate. There's what's called the one that I'm counting is 13.2 billion years. It's called the light travel distance. How long would light have had to travel for me to be seeing it now? But the second question is, if the light left now, how far would it have to travel to get to me? And then there's a distance of, if light could somehow travel instantaneously instead of the speed of light, what's that distance? And those are all different numbers. And they mean slightly different things. Yeah?
Does it even make sense to think in this three-dimensional way how big something is? Because if we knew that, then what's around it?
Yeah. No, it doesn't. Okay. So the one that makes the most sense is this light travel distance.
Yeah.
And the reason it makes the most sense is that because if I was in different positions compared to it, the light travel distance would work the same. The light travel distance is the same for different parts of space, basically. The other ones can change based on how my problem is set up. Who hasn't asked a question yet? The white shirt.
Yeah, I was a little surprised that you got through the first lecture, didn't mention inflation. So, am I wrong? Well, am I wrong? Because I thought that anisotropy was a consequence of inflation, or is it just the magnitude of this?
Sorry, say that one more time.
The anisotropy of the microwave background, I thought was a consequence of inflation, or at the very least, the magnitude of it.
If you can have anisotropies in the cosmic microwave background that look the same without inflation. Inflation can, in certain inflation scenarios, it can make imprints on what the cosmic microwave background looks like, and it's at details that are smaller. So this is what this bicep experiment was looking for. Was very small changes in the angular correlations of between different points in a circular pattern. And that is something that inflation can produce. So inflation can affect how we see the cosmic microwave background. But in a universe that doesn't have inflation, you can also have the cosmic microwave background. It's itself not proof of inflation that there is a cosmic microwave background with anisotropies. But if you really well measured stuff, you could potentially look for inflation properties.
With respect to the redshift phenomenon, you were showing were some absorption lines. I assume they were hydrogen.
Yes.
Okay. But as they shift, they would impinge on emission lines from other materials. how do you know that that is just a redshift?
Yeah, so what I was describing with not going into a lot of detail is called the Linden alpha background. So you saw each material had a bunch of different absorptions. There's one that is by far the most important. It's called the Linden alpha absorption. It's the one that moves an electron from the first energy state of hydrogen to the second energy state. That's the most important one in the universe for two reasons. There's more hydrogen than there is anything else. It's like 90% of everything, and it's the brightest thing in the hydrogen line. So what you get is, what you study is what's called the Linden alpha forest. So if I had my source here and it had a spectrum, my source is over here. Well, actually, I'm making this thing. I have a spectrum that's constant, or it looks like a black body or something like that, right? I'm missing, if I had just a gas cloud here, I'd be missing this line from the Linden alpha absorption. And if I had more gas over here, I would get this. But as you said, it gets confusing. Because really, there's a little bit of gas everywhere.
Right.
So what I get are peaks, where my absorption looks like this. There was a lot of gas here, there was less over here, there was here, and you get this like line from Linden alpha. And that's called the Linden alpha forest, because if you look at it upside down, it looks like trees.
Okay.
Yeah, so you get a little bit of absorption everywhere, and where you get that absorption tells you how much gas there was at every distance.
So are you doing this statistical analysis then to get the actual point of the lines?
Yeah, so what you do is you look at your source, and you get this little foresty thing in your telescope, and then you do the redshift for each point in it, and then you also, to get the answer right, you have to worry about all those little lines that were less bright, but also exist, and then you have a computer that calculates the best fit to all of that.
Okay.
And so it's complicated.
Thank you.
Has everyone asked a question? Is there someone that,
I didn't really understand the Compton scattering, and I tried to read this before, and I'm not really a physicist, I don't know anything about like inelastic scattering. Like, why is it that you can add like part of a photon's energy, increase it or decrease it, but like it seems like photons should be just absorbed or not absorbed, but then sometimes that's not true. Like
So imagine that you have a photon and it strikes. So here's an atom, and there's something in some energy state. We'll say that's in the second state, right? So here's this, the first orbital. The second orbital is the one the electron's in. There's a third orbital. I have a photon come in, and it bounces this from the first to the third orbital, and it took that amount of energy to do. That was the photon coming in.
Is that an absorption like that?
So this gets absorbed, this moves up. Yeah, so this gets absorbed, this moves up. And we'll just say it's the exact amount of energy. If it's not, then you'll need a photon to come off.
Yeah, that part makes sense.
Yeah. Then this thing comes back, and instead of going to the second, it goes all the way back down to the first state. So it emits a photon, and this photon is a higher energy than this photon because it moves more states.
Right.
And it's really just, is this the same photon or a different photon? It doesn't actually matter.
So it gets absorbed, and then later it gets re-emitted.
So in that situation, that's what happens. But I can also have just, so for the inverse, so that's a scenario where I have a photon come in at one energy and come out at another energy.
Right.
And you could call those two different photons that got absorbed and then got re-emitted, but it doesn't actually matter that you call it that.
Okay.
It could have been emitted and then absorbed in the same way, because you started in a scenario, you ended in a scenario, and who cares what happened in the middle. So in the inverse Compton scenario, I have a photon come in at a specific wavelength like this. I have an electron that's coming in at a really high velocity towards that photon. And remember when I said redshifting?
Free electron, not like spinning around.
No, just a free electron. Remember when I talked about redshifting? It was because things are moving away from us that they got redshifted. This is moving towards this really, really, really quickly, which means to this it looks a blue shift. So this is the wavelength of the photon that I see, but the wavelength that the photon sees is something that looks like this. So these bounce off of each other, and now in this new state, this thing now looks like this, right? So they exchange energy in my frame. Because they looked like an elastic just bounce off scattering, but they only looked like a bounce off scattering in this sort of.
But it never gets absorbed and re-emitted in that case.
It does or it doesn't. It doesn't actually matter. It's just kind of a tricky way of saying that. Yeah. I got time for maybe one or two more questions. So who has asked? You haven't asked a question, right?
Me.
Yeah.
Okay. Considering Bremsstrahlung radiation, synchrotron radiation, and inverse Compton effect, in addition to the, at the beginning of the Big Bang, why were there free photons around?
So why are there free photons?
Yeah, were they created in the Big Bang, or are they the result of interactions between the particles?
So the Big Bang produces an enormous amount of energy, probably an inflation. If we think that's true, all that energy eventually goes into an inflation field at some point. And that point is like 10 to the minus billionth of a billionth of a billionth of a billionth of a second after the Big Bang. So it really quickly moves into this inflation field, and then it moves out. And the energy just basically populates the electromagnetic field, the gravitational field, those fluctuations at this point are wild. Some of those fluctuations become particles. Some of the fluctuations are very energetic fluctuations. Some of them are light. So basically anything that can be excited, and this is, so quantum field theory, says that everything is some excitation of a field. And so when I dump energy into the field, I make particles and I make fields that go crazy, right? And I do both. Anything that can be created when I have a tremendous amount of energy is created. So that happens in the Big Bang. That's why we use particle colliders. We just crash two things into each other to produce a bunch of energy, and then everything that can come out comes out in different numbers. I mean, how frequently a photon is created versus other stuff depends on physics, but that's the thing. I have a tremendous amount of energy, so I can create everything.
So it's the congealing of energy that turns into all the particles and photons.
I think that's a reasonable way of thinking. So one last question, does anyone have? Okay, sure.
So I'm trying to sort out the different ways that light photons are created, and I've had a long time question about the black body radiation concept. So you have the diagram you did there, which was in your slides, which is the classic illustration of what quantum theory is all about. Transitions between energy levels in an atom. And I presume that if you have a minimum energy level required for a transition and you have a photon with a higher energy level, but not so much to produce two levels, that it could go one level and there'd be something left over.
There'll be a photon that comes out.
Okay. In black body radiation, I've read a lot of stuff trying to figure out what physicists think about it, and I come away, one of which is the famous Russian series, Lifshitz and whatever, and they say essentially in the 50s or 60s when they wrote it, we don't know how black body radiation is created, but it doesn't matter because we know the statistical law, and here's the curve. The question is, so black body radiation does not seem to correspond to these individual transitions, at least as far as I've ever heard or been able to figure out, and it's something else.
It's a thermal, wiggle, basically. So I'd have to think about this a little bit to get it right. But you have all the materials are bouncing off of each other. Some of them it's going to excite move transitions. Some of it is just the atom stays intact, bounces off another atom, and it moves separate ways and you get photons. So there's a lot of different emission that's happening. I'll have to think about that, but I'll answer next. to give you a correct answer.
Well,
you can get back to us.
So.
I'll get back to you. Okay. Thank you.
Well, thank you.